Hello friends, I welcome you in lecture number 4 on infinite series. In this lecture, we are going to discuss the integral test to check the convergence of particular type of series. So first we understand what is integral test, and then we will see how to apply the integral test to decide the convergence. So suppose we are given some infinite series, say sigma an, where n is given as n equal to 1 to infinity. So the idea of integral test is we define a function fx on the interval which starts from 1, and here there is no upper bound. So here range of summation is from n equal to 1 to infinity. So we consider function fx as defined on closed interval 1 to open interval infinity, and this function is decided from the nth term of the series by replacing n by x. So this function has value at n, f of n is equal to an. Suppose we have an equal to say log n divided by n, then function we will determine as log x by x. So we replace n by x in the nth term and we construct the function fx, so that f of n equal to nth term of the series. So we are given some series, say sigma an, and we first determine the function fx by replacing n by x in the nth term of the series. Now to apply the integral test, this function must be positive, that is value of function must be greater than 0 for every x in this interval. Second requirement is function must be continuous on closed interval 1 to open interval infinity. And third requirement is function is decreasing on closed open interval 1 to infinity. So if our function f, which we have constructed from the nth term, is positive, continuous and decreasing on closed open interval 1 to infinity, then we can apply integral test. So suppose our function is positive, continuous and decreasing on closed interval in 1 to infinity, then we will check the convergence of improper integral 1 to infinity fx dx. So if this improper integral is convergent, then given series is convergent. If integral is convergent, sigma an is convergent, and if this improper integral is divergent, given series sigma an is divergent. So convergence or divergence of series sigma an depends on the convergence or divergence of this improper integral of function fx, where our function is positive, continuous and decreasing on closed open interval 1 to infinity. So this is the statement of integral test. To apply integral test, first we have to check whether this function is positive, continuous and decreasing. For decreasing function, we can use the derivative. We know that if first derivative of function is positive on closed interval 1 to infinity, then it is increasing, and if first derivative is negative on the interval 1 to infinity, then function is decreasing. So to check whether function is decreasing or not, we can find out its first derivative, and if first derivative is negative on close open interval 1 to infinity, then function is decreasing on close open interval 1 to infinity. Now to apply integral test, it is not necessary that we start with n equal to 1. Suppose our series is given from say n equal to 4 to infinity, then in that case we can start with integral from 4 to infinity, and we will check the convergence or divergence of improper integral with limits from 4 to infinity. Now sometimes what happens, our series is from 1 to infinity, but our function is decreasing on some natural number, say n to infinity. So it is like this. Suppose we have 1, 2, 3 up to say capital N, and our function is decreasing on this interval. So this is also allowed if our function is not decreasing on 1 to infinity, but if it is decreasing after some number n, then also we can apply integral test. So what we require is our function is ultimately decreasing on this type of intervals. There must be some natural number capital N such that our function is decreasing on this interval for which x is greater than capital N. So for larger n, our function must be decreasing. So we will remember all these conditions to apply integral test. So first we understand the statement of integral test, and then we discuss some examples on integral test. So let me find out. This is the lecture number 4. Here we have written all these things. The integral test. Suppose that function f is a continuous positive decreasing function on close open interval 1 to infinity, and let a n equal to f of n. So our function is constructed from the series, from the nth term of the series. We replace n by x in the nth term, and we construct this function fx such that nth term equal to value of this function at x equal to n. So suppose that f is a continuous positive decreasing function on closing open interval 1 to infinity, and let an equal to f of n, then the series sigma an is convergent if and only if the improper integral 1 to infinity fx dx is convergent. So in other words, if this improper integral is convergent, sigma an is convergent, and if this improper integral is divergent, sigma an is divergent. So we understand the application of integral test with the example. Here we are asked to determine the convergence of the series sigma 1 over n square plus 1, n is from 1 to infinity. So first we write down nth term of the series, which is 1 over n square plus 1. Now we construct the function fx by replacing n by x in the nth term. So nth term is 1 over n square plus 1. So we consider fx equal to 1 over x square plus 1. And in the series n is given from 1 to infinity. So we consider function on close open interval 1 to infinity. Now here we can see x square is always positive on this interval because x starts from 1. So it is 1 square plus 1, 2 square plus 1, and so on. So clearly our function is positive on this interval. Also it is continuous on this interval. It is division of two continuous functions. X square plus 1 is polynomial function, therefore it is continuous. This is constant function, therefore it is continuous, and we know that a quotient of two continuous functions is continuous if quotient is non-zero. So here x square plus 1 will never be 0 because x is starting from 1. So fx is continuous on closed interval 1 to infinity. Clearly fx is positive for all x belongs to closed open interval 1 to infinity, therefore f is positive on closed open interval 1 to infinity. Again it is clear that f is continuous on closed open interval 1 to infinity. And from the formula of function it is obvious that function is decreasing, because if we increase the value of x, fx is going to decrease. Or we can check its derivative. So we consider derivative of 1 over x square plus 1, which is minus 1 over x square plus 1 square into derivative of x square plus 1 in the product. This is by chain rule, and this we can rewrite as minus 2x divided by x square plus 1 whole square. And because x is starting from 1 to infinity, this x is always positive. This is also positive for all x, and due to negative sign this is less than 0 for every x in this interval. So therefore first derivative of fx is negative for all x in this interval, therefore f is decreasing on closed open interval 1 to infinity. So we can apply integral test because this function f is positive, continuous and decreasing on closed open interval 1 to infinity. So now we check the convergence of this integral from 1 to infinity of a function fx. So here we put fx equal to 1 by x square plus 1. Now here this is improper integral of first type, so we replace upper limit by b and we consider limit as b tends to infinity. Now integral of 1 over x square plus 1 is tan inverse x. So we write tan inverse x, x is from 1 to b. Now upper limit is x equal to b, so we have limit of tan inverse b minus tan inverse 1 as b tends to infinity. Now tan inverse 1 is pi by 4, so we have tan inverse b minus pi by 4. And if we consider b tending to infinity, we have tan inverse infinity minus pi by 4, and tan inverse infinity is pi by 2, so we have pi by 2 minus pi by 4, which is nothing but pi by 4. So value of improper integral is finite real number, therefore this improper integral is convergent, and therefore by integral test sigma 1 by n square plus 1 is also convergent. We consider one more example. Determine whether this series sigma log n over n converges or diverges. So first we write down given series is sigma log n by n is from 1 to infinity, and function fx is obtained by replacing n by x in this nth term. So nth term is an equal to log n divided by n, and we consider fx equal to log x divided by x. Here n is starting from 1, so we consider x belongs to closed open interval 1 to infinity. Now here fx is log x by x, x is starting from 1 to infinity, so x is already positive, and if we consider x equal to 1, log 1 is 0, but if we go beyond x equal to 1, we know the graph of logarithmic function, it is like this. So at this point log x is 0, but if we consider all these points, then at all these points log x is greater than 0. So clearly this function is positive on open close interval 1 to infinity, because at x equal to 1 it is 0. because log 1 is 0. So the function f is positive and it is obviously continuous for x greater than 1 because x is continuous and log x is continuous function. So the function f is positive and continuous for x greater than 1 because log x is continuous and positive for x greater than 1. Now for decreasing, we first consider first derivative of function fx. So derivative of log x by x with respect to x, we apply division rule here. In the denominator we write x square, in the numerator x as it is, derivative of log x which is 1 by x minus log x as it is, derivative of x is 1. Now here x is starting from 1, so it is non-zero, so we can cancel out and we have 1 minus log x divided by x square. Now x square is always positive because x is starting from 1 and 1 minus log x, so we require f dash to be negative. So because x square is always positive, f dash is negative if 1 minus log x is negative. That means if 1 is less than log x, that means if e is less than e raised to log x which is equal to x, that is if x is greater than e, function f is decreasing. So our function f is decreasing on open close interval e to infinity. So our function is starting from 1 but it is decreasing from this point. So for integral test we don't require that function is decreasing from this point. We require that we must find at least one integer such that function is decreasing at every point in this interval which is open close interval e to infinity. So here f dash x is negative if x is greater than e, therefore f is decreasing on this interval. So we have our function is decreasing on e to infinity. Our function is defined from 1 to infinity, but as we discussed, if we can find out some point such that after that point our function is decreasing, then also we can apply integral test. Here that point is e. So if we consider this interval from e to infinity, then function is decreasing on that interval, so we can apply integral test. Now to check the convergence of series, we check the convergence of this improper integral from 1 to infinity fx dx. So here log x by x dx. Now this is improper integral, so we replace infinity by b and we consider limit as b tends to infinity. Now we can rewrite log x by x as log x into 1 by x, and 1 by x is nothing but derivative of log x. So here we have this type of things, f dash x fx raised to n into derivative of fx dx. If we have this type of situation, then integral has the value fx raised to n plus 1 over n plus 1. N is not equal to minus 1. So here we have fx equal to log x and we have its derivative in the product. So we can have value of this integral is equal to log x whole square divided by 2. So we have used this formula. Fx is log x, its derivative is 1 by x, which is written as d by dx of log x. So this is equal to fx raised to n plus 1. Now here power of log x is 1, so log x raised to 1 plus 1, which is 2 divided by 2. Now if we put x equal to b, we have log b whole square divided by 2 minus log 1, which is going to be 0. And if we take b tending to infinity, we have log infinity, which is infinity, and infinity square is going to be infinity divided by 2. So this improper integral is divergent because we obtain this infinity, and therefore by integral test this series is also divergent. So this is all about integral test. I hope you are able to apply integral test. What you have to remember is whatever function we construct, that must be positive, continuous and decreasing on given interval. So this is all about this session. I hope you like this. Thank you very much.